Hello, good evening, everyone, and welcome to CAWASA Webinar 2021 Series number 20. I'm Ignatius Jean, the Executive Director at CAWASA. Today, we are going to examine the topic, water separation controls and monitoring for reverse osmosis desalination plants. And this will be presented by Mr. Chip Westaby, who is the sales manager for the Turner Designs hydrocarbon instruments, a worldwide leader in fluorescence online monitors for oil and algae measurement. With over 20 years experience in oil, water separation controls and monitoring, Chip has worked in refineries, oil field desalination plants, power plants, etc. He has presented at international water conferences, been published numerous times, and focuses on field experiences. Reverse osmosis desalination plants have become significantly more popular in the last 15 years, to operating costs being reduced significantly. Large municipal and industrial plants have been installed throughout the Caribbean. When these plants are near industrial facilities or shipping channels, oil spills can cause significant damage to the reverse osmosis membranes. Algae blooms can also cause fouling that increases the operating costs of the plant. Both fuels and algae can be detected by fluorescence monitors to alert the plant operators that additional intake water treatment is needed to protect the membranes. The same fluorescence technology can also help industrial wastewater plant operators quickly identify upset conditions and when high oil can be discharged from the plant. This presentation will review the causes of membrane fouling, methods of preventing significant issues, and how to detect fuels and algae reliability. There will be a discussion of how to have a low maintenance operations in dirty industrial wastewater and utility cooling water. I now hand over to our guest presenter, Mr. Chip Westaby. Over to you, Chip.
Thank you, Ignatius. I really appreciate the opportunity to speak with your group and colleagues here. We work with Rose Environmental out of Trinidad, and Abigail Ali let me know yesterday that there was an opportunity to present, and we had been wanting to visit with your group for a little while now. So when the opportunity was available, we really appreciate this, and hopefully we'll be able to talk about a few things that are interesting or novel and pertinent to some of the water operations throughout your Caribbean region. Some of this may be a little bit new, but is things that are processes and devices that are operating in the environments that you have. So I'm going to share my presentation here. And I think this should work properly. All right, can everybody see my presentation here?
Yes, we've got you.
Yes, we can.
Wonderful, thank you so much. Again, my name is Chip Westaby. I'm the sales manager for Turner Designs hydrocarbon instruments. We are a US-based company. I am in St. Louis, Missouri today. I wish I was somewhere in the Caribbean because it's generally more scenic than where I am. And someday I hope to get down there to visit. Actually, I was making some plans about 2-3 weeks ago for a vacation. It might not be for a year or two, but we will get down there at some point in time. I've been working with Turner Designs about 15 years. I was working for a different company prior to this that also did oil water measurement. We did interface control Turner Designs focuses on parts per million measurement. So we are in water processes where we're looking for contaminants, and we focus primarily on oils, but in some places we do algae measurement as well. So just a real quick background on our history in desalination plants. Our company as a whole has focused on industrial wastewater for our history, which is over 20 years. Though there are about 100 of our devices installed at various places around the world looking at intake water. Most of those are going to be a desalination plant where it's seawater processes, but there are a number of places around the world where we are in freshwater looking for oil spills. So these are primarily along major navigable rivers like the Mississippi, the Ohio River near Detroit, the Danube in Europe, and some of the rivers in China. For desalination plants, most of the installations on the larger plants, places where a small amount of oil fouling or algae fouling can cause a significant amount of cost due to the number of membrane canisters that may be present, or they happen to be in areas where the operator of the plant needs something to protect themselves from costs. So sometimes the municipal companies will operate the plants, sometime a third party will operate them. And so it kind of goes into the commercial discussions as to who pays for what, and that's how you decide what to do. Primarily, we focus on all industries in designing instrumentation and technology that is highly rugged so that it will operate for a long period of time, something that is easy to operate and has high sensitivity so that you get good performance in the process that we're looking at. So a little bit on our technology. All of our products use fluorescence measurement to measure the constituent that we're looking for. I mentioned that we focus primarily on oil, so we will be talking about oil quite a lot in this presentation. All of the details as far as oil measurement also are true for measurement of chlorophyll, which is a primary component within algae. The only difference as far as a measurement standpoint is the type of light source used in the measurement. All the other details are the same. So the way that fluorescence works is we start off with a light source. For oils or hydrocarbons or fuels, the light source is going to be ultraviolet. It's really hard for us to make a demonstration in ultraviolet to show how things are measured because nobody can see ultraviolet. But in the little picture that we have here, we have got a different light source and a different type of fluorescent response in visible light, so we can kind of talk about how this works. But in simple terms, we have a light source. Water is exposed to that light source. Any oil that's present in that will absorb some of the light, and they will spontaneously emit a different wavelength or a different color of light. So this response is instantaneous. It is a nanosecond response, and it is continuous. So we have the ability to make these things for sample analyzers, so you can do a manual measurement, but most of them are continuous online instruments. The light stays on continuously, water flows through the devices continuously, and we make a light measurement continuously. So primarily the sensor, the device is actually making the measurement, is a light intensity sensor. It's just tells us how bright the light is. The more oil, the more chlorophyll present in the water, the brighter it is. Things that are not oil, or in the case of when we're measuring algae, things that are not algae don't produce a response because they may fluoresce at different wavelengths. For instance, we can actually measure the presence of algae when there's oil present, And we can measure presence of oil when there's algae present because they respond at totally different wavelengths there. Solids, gas bubbles, other chemicals, salt, whatever you name it, won't produce a response because they're not going to produce that fluorescence response with the light source and the light detector we're looking at. So in my little picture here, the bright green light is actually a dye that's been added to the water. It's a known type of dye. It's very similar to what's put into antifreeze inside of a car to produce a bright green or a bright orange color. So we're using that as a surrogate for oil. So that dye is absorbing the blue light and emits green light. So the way that our sensors are set up is we have an optical filter between the sample and the sensor. And the optical filter filters out any of the light from the light source so that only light generated by the target, by the oil or the chlorophyll, is actually measured. Anything else that's reflected or absorbed or somehow gets into the process is not measured. So it is a very specific measurement to oils or hydrocarbons or chlorophyll with very little other interferences. So places where these are used, I mentioned that primarily as far as the history of our company was for industrial wastewater, because virtually every power plant or refinery or oil field has to have some type of rainwater runoff or wastewater. And because there's a high chance there could be oil present, the local governments, the EPA, Coast Guard, or whomever, make sure that water is clean. And there has to be a certain monitoring for that. So it's a very common requirement for industrial plants to have some type of monitoring. Most of them are going to do it manually, grab a sample once every month or 6 months. But for the bigger plants, the places where things are a little more sensitive, they will put continuous instruments in there. Other places that they are used are for detection of leaks. You can have a lube oil or hydraulic oil within a power plant leak into cooling water, or in a refinery, or in a power plant that has heavy fuel oil. There may be steam processes. They're heating up those, and we can measure leaks. From a measurement standpoint, these are all basically the same measurements, the same setup of the instrument. But we also do, I mentioned, intake monitoring. So for freshwater or seawater, it's not an industrial process, there's no expectation that there's oil present. And so for those cases, we're looking at processes that have no response. There's no oil in the water. We're getting no response at all. And the devices or the technology is quite sensitive in that case. You have to kind of imagine that this device is like you sitting in a dark closet or an interior room of your house. If you shut all the doors and windows, it goes extremely dark and black inside those rooms. And if you turn on a small LED on the other side of the room, you would see that extremely easily because it's a light and an overall black background. And so that's how our devices work in clean water processes. When there's no hydrocarbons and no oil present, the water's falling through the device. There's no response being made. But the moment a small amount of oil shows up, it's like the LED on the other side of the room. The sensor sees it super easy because there's nothing interfering with the measurement. All of a sudden you have some glow or some indication that there's something present there. And I'll give you a quick, easy indication of a leak. For measuring of algae, it's a different scenario. There's always algae present in the water. So the device is always seeing some type of response. It's always giving you some type of indication, but it will definitely trend with the changing of algae concentration in intake waters. So why do and where do most of the desalination plants measure oil for intake or the algae? Well, this is a generic mock-up of a desalination or other intake process. I'm certain that every place is a little bit different. So this is just generic indication. So you have an intake channel, you have a discharge channel. some type of screen, some multimedia, particle filtrations, sand filtrations, maybe a flotation cell to clean up the water a little further after all of the filters have taken place. And ultimately, you get down to a point where you have seawater with little to no particulates in it. It's basically just got whatever's dissolved in the seawater that goes through the reverse osmosis membranes, producing fresh water, and then the reject, the concentrate, returns back into the ocean. So there's a lot of different things that are analyzed here. Usually conductivity, turbidity, and pH are very, very common, and there's heaps of ways to do that. And they'll be measured at lots of different places throughout the desalination plant. There are some specific ions analyzed for, and that's a little bit different depending on the location and the type of plant design. But ammonium, iron, manganese are common analytes in desalination plant. And then, while a lot of these other analyzers, there'll be 5 to 10 to 20 of them throughout a plant. Usually for oil, there's only a single point of measurement, possibly at the very intake. You want to try and detect any oil as soon as possible to give yourself as much forewarning and advanced notice as possible. But you also kind of want to measure right before the membranes themselves. Any pumps that may have had a leak along the way, or any extraneous sources of oil that may have come into the process, you want to see that, because these reverse osmosis membranes can be extremely sensitive to the presence of oil. For algae, the membranes are not as sensitive. It's relatively easy to clean a membrane off with a clean in place system, and maybe a little bit of an acid or bleached system. So it's not as pertinent to measure algae as oil, but there is always algae present. So usually right at the intake is where the algae is measured. Because there's always some algae present there, the screens and the filters are there to remove all the particulate, including algae. But when the goal of this device is to indicate upsets, to know when there's been an algae bloom. Maybe the wind changed direction and now it's blowing a whole big mass of plankton into the intake. If there's phytoplankton or zooplankton present, they all kind of follow the same currents. And so when the device is looking for, it's primarily the phytoplankton, the plant-based algae planktons, it will indicate to you that there's been some type of bloom present, that something has changed. The measurement will increase, and now you know that your filters might be plugged a bit too quickly, or you may need to turn on your DAF system, the dissolved air flotation cell. A lot of plants don't like to run the DAF system continuously because it's an energy consumption. There's chemicals added in the DAF, and so when the algae is normal, when there's no oil present there, you may not need to operate those things or reduce the operating costs, and then you turn them back on or increase the use of them when the upsets are occurring. Because the response of these devices is instantaneous, it can be quite easy to optimize the chemical additions or the DAF usage based off their indications. So in asking around to different people who operate, people who build desalination plants, and even the people who design or build the membranes themselves, I've asked them, what parameters that are not easy to measure are important to you. And silt density index, oils or fuels are important. Algae is important. I mentioned turbidity and pH and all that. Obviously, those are very important, but frankly, they're a little more easy to measure. So we focus on the oil. We focus on the algae. Most of the projects that we have worked on have had a required oil spec somewhere between 100 parts per billion, which is 0.1 part per million, and about 10 parts per million. Commonly, 1 part per million becomes the threshold for indication or threshold for alarming of oil. I asked a couple of questions along the line as to what this means. And the reason I do this is that without some type of online instrument, regardless of the design of it, the only way to measure oil is manually grabbing a sample in a jar and taking that jar to a laboratory, analyzing the oil concentration in that jar, producing a response and saying, all right, we are at a half a part per million or 0.1 part per million, something like that. But these laboratory methods take hours to days to produce a result. So it's not likely somebody's going to do it regularly. And it's not likely somebody's going to be able to catch an oil spill or an upset just as it starts to occur. So there's a time needed here. And so 0.1 or 1 part per million or 10 parts per million for a couple of seconds is an entirely different scenario than 1 part per million for a day or a week or a month. They're two totally different scenarios. The longer the oil spill is present, at whatever concentration, the more volume of oil is in the process, the more likely you are to have damage to your membranes. These fluorescence instruments being instantaneous, producing a fast response, you'll see the very beginning of a oil spill or algae bloom or whatever has happened there and can prevent damage to the membranes. So our devices and most fluorescence devices can measure low concentrations like this. And so whether we're at 0.1, 1 or 10 ppm, the fast response is really the pertinent factor in protecting membranes. As far as algae goes, because algae is not a generic substance, there's tens of thousands of different plant and animal species that are called algae or are called plankton. Each one is a totally different piece of chemistry and biology. So from a sensor standpoint, we produce a generic response. And so some are going to have much, much higher responses than others. When we set these things up for measuring chlorophyll A, we're looking at the most common chlorophyll that is in the largest range of phytoplankton or algae that can be in the water. And for those, most of the time we've seen the requirement of less than 500 milligrams per cubic meter, which is about 500 ppm, or sorry, 0.5 ppm. The real need for response is just change. If we're measuring at 10 or 20 or 30 most of the time, and it goes up to 100, 200, 300, that's that change. That's the leading edge of an upset or a bloom, and when things have to be changed. And something to keep in mind here is that every facility is going to be a little bit different. Some locations, the water is more shallow. In some cases, the water, the currents are a little bit different. So the range of these algae and plankton are going to be very different all parts of the world. So these are very generic terms. So speaking just a little bit on the DAF unit, because this is the primary device that has allowed some desalinations to be effective, because they are very, very capable of producing clean water prior to the membranes, and they do cause a lot of cost. So we see where the water comes in on the influent side here, that there's a couple of contaminants in there. They're going to go through these corrugated angled plates, and then air bubbles are going to come up from the bottom. Those air bubbles will grab any particles, either be solids or they'll be algae or oil, and they'll float them to the top because they're directly in contact with those particles. The smaller the air droplet or air bubble, the easier it is for it to grab something and float it. So that's why they're called dissolved air flotation cells, because the oil droplets are so small that they are actually considered to be dissolved within the process. And when they get inside the separator, they start to coalesce, they bump into each other, they form larger droplets, they bump into the oil, they bump into the algae, they form larger particles. And the larger the particle, the easier it is to float. And eventually it's all skimmed off and removed. But because of the amount of energy needed to produce the compressed air, to produce the dissolved air, to recirculate the water, if there's any chemicals added to it, those are the kind of things that are costs. And if your water is clean and operating smoothly, you may not need to operate the DAF at all. You can bypass it and then go off to normal operations. Other facilities have a slightly different design. Some facilities we work with may have two separate intakes, one at a high level, one at a low level. Some of these plants prefer to operate at the higher position because it's easier to intake water than at a lower position. And so if there's a detection of oil or algae, maybe you change the intake position. And in some cases, you just have to shut down the intake entirely because you don't have a DAF system. You may only have one intake, or you've already switched and you're still seeing oil or algae present. So this process controllability at changing conditions is what we're helping with here. So real quickly, just show you just a little bit of what these products look like. We have a suite of different products to be used. The most common one for desalination is what we call a TD120. It is designed specifically for the desalination market. It's a very simple design. The water is actually analyzed on this little box on the right-hand side here, which says deep UV. That's the type of ultraviolet light source that we use. It is all corrosion resistant in seawater. It has a calibrated range of 0 to 1 parts per million, and it'll detect any fuel, lubricant, crude oil, or other hydrocarbons in the water. We commonly see marine diesel as the most likely source of contaminant because every ship that passes in front of a desalination plant or near there has marine diesel as their fuel source. Some may be cargo containers that are going to have fuels on them, maybe a crude oil tanker, but all your cruise ships, all your container ships, all that kind of stuff, marine diesel is their fuel. So that's the most likely source. And so that's usually what we do our calibration to. For algae, we have a slightly different product. I mentioned it uses the same technology, but a slightly different format. And so this one is still all corrosion resistant. It still has has a visible light source instead of ultraviolet. And the range is 0 to 100 micrograms per liter of chlorophyll. For freshwater, we would do a slightly higher range, but for seawater, 0 to 100 is the common range. What we've seen is usually globally 2 to 10 micrograms per liter of chlorophyll A is what is common in seawater. So 100 micrograms per liter is 10 times normal, which would obviously be a significant bloom. So both the TD120 and the CF200 have a similar format. Water comes in one side, goes out the other side with a light source right there in the middle, and then display an indicator of the constituent being measured. So I mentioned we do a little bit of wastewater, and we might talk about it at the end. So this is a picture of an installation in an industrial wastewater plant. I recognize it's hard to see, but you may see up on the left-hand side here that there is a small plant. I'm sorry, I'm trying to turn on my my pointer. Here. So over here, there's a little industrial plant. Back here, there's a parking lot. So this river is actually the industrial outfall of the plant. It is flowing into a major river just off to the left-hand side here. And this little walkway that you're seeing is actually a weir. So the water actually goes underneath that, trapping all the oil and other things that float upstream of that. And then there's a lagoon and finally outfall to the river. So this is a demonstration that we put on a couple of years ago for a customer to demonstrate low maintenance operation and high sensitivity. So after a month of service in this very dirty, murky, turbid water, this oil water monitor was clean. The primary feature of this is you can see here, we have this piping assembly right here. And then the water comes out of the piping assembly, runs through this little tube and back down into the flow cell. Once it reaches that flow cell, it falls freely through the flow cell with no contact to the optical surfaces. Without any contact, the device doesn't get dirty. And so in operating in a process like this dirty water, we measured between 10 and 30 parts per million of oil for 30 days without it needing to be cleaned at all. Any power plant or steel mill or other industrial facility can have similar types of operations. Oil fields, refineries, we can operate very low maintenance in them as well. Their water tends to be a little bit more dirty, so maybe we need a little more cleaning at that point in time. So let me go to my next screen. Oops. I thought I was erasing these things. There we go. All right, so then the other place our device are used primarily is in power plants, both in the cooling water and then in steam loops that are used to heat up fuel oil. So this is one of my favorite pictures of a power plant. This is in South Florida. This actually got a nuclear plant as well as a fossil fuel plant at the same spot. And then they have a lagoon as well as a catchment basin in the back. So this plant is very flexible. It can pull cooling water from the lagoon. It can pull cooling water from the catchment basin in the back there. On the right-hand side, they're building a cooling tower. So it's got a very flexible design. You could see here that if they are using the lagoon for cooling water and you have a heat exchanger leak, the water would go from the lagoon into the heat exchanger where the leak is occurring, and then the water will go right back out into the lagoon, contaminating the environment. In the catchment basin in the back, it will still contaminate that. It's obviously owned by the plant, but they don't want to contaminate that. It's open to the environment. Likewise, even in the cooling towers, they don't want to get those things dirty because they have to use chemicals to clean them up. And the oil is a food source for algae. There are cooling towers that are monitored for algae as well, because algae blooms in cooling towers are very easy. It's a hot water source and there's sunlight, so algae blooms there. Biocides are expensive, so if you have a bloom, if you know you have oil, you can control your consumption of chemicals. Excuse me. And if I remember right, various places around the Caribbean, there are power plants that are using fuel oil as the fossil fuel source. Often those are heated, sometimes with steam directly from the power plant. And the heavy fuel oil, if it does get into the steam processes, is something that should be detected. So our technology and our products could work in those places as well. So that's quick overview of how fluorescence works, how fluorescence can be used in various industrial plants, what it does to help operations, and it brings me to the end of my my presentation here. So certainly can open this up to questions or comments or whatever the rest of your meeting may be. So Ignatius?
Yeah, thank you, Chip. Well, the floor is open, and thank you for this insight into some of what you offer in terms of your products and some of the technologies that you have for mainly people with the RO systems. So I'd now have the floor open to any questions or comments from the participants. Not seen anyone.
Chip, this is Gary.
Hi, Gary.
I will see if I could get the ball rolling with some questions.
Sure.
I just had a question for you. When you were talking about the algae, you stated that the CF200 for the saltwater applications is set at a much lower, I guess, sensitivity than if you were doing freshwater applications.
Yep.
What is the reason for that? Is there just generally more algae in freshwater?
That is the primary reason. There tends to be a different species or different types of species of algae in freshwater as well. It's a different environment, so different plant species will live there, and you can imagine a pond, a freshwater pond tends to be quite green and kind of murky, and so that would be a significantly higher concentration of algae than the ocean would be. Even if the ocean is green, it does not have nearly as much algae present as a pond would. Rivers tend to be pretty clean themselves, but once you put it, once you catch fresh water in a basin, it can grow algae a lot quicker. So it's just the nature of the type of species as well as the type of concentrations that can be present.
Okay, so yeah, so the desal application is really that lower range measurement.
Yep. Mm-hmm.
Okay, cool.
Yep. Now, I know there's some desalination plants in Trinidad, and I haven't done a tremendous amount of research, but are there other, operating desalination plants on other islands throughout the Caribbean?
Yeah, pretty much up in Antigua, I think Barbados, you would find plants in the British Virgin Islands, the USVI, the Bahamas, most of the northern islands in the Eastern Caribbean archipelago would be doing desal. There are some small systems that managed or operated by some of the hotel plants as well.
Sure.
Yeah.
So the resorts try to have their own dedicated source to ensure continuous water supply.
Yeah.
The plants that are existing, are they reverse osmosis or are they thermal distillation?
To the best of my knowledge, most of the new plants and most people have gone reverse osmosis systems now. Yeah, I think the people have migrated or have been migrating away from the thermal systems.
Yeah.
To RO
that makes
systems.
sense.
Yeah.
I know we've done a very small amount of work with the U.S. Navy in Cuba at the Guantanamo Bay, and they had a thermal system up until a few years ago, I think, and they replaced it with reverse osmosis at that time.
Yeah, the most of the and there are several companies where they produce bulk water and sell to the utilities. So, for example, on Cayman Islands, the Bahamas, most of the islands there, they do have various suppliers of reverse osmosis water. They sell bulk water to the utilities do distribution. Yeah.
Okay. And those like what I consider like a third-party operator, someone like Suez or Veolia or somebody like that's operating them.
Yeah, you would have those third parties such as I think Consolidated Water, Seven Seas, etc.
Okay.
Name a few.
Excellent. Thank you.
Yeah.
Any other questions from the group? Okay.
Any questions, guys? Now's your time.
Chip, Gary again.
Sure.
Okay. Go ahead, Gary.
Yeah, just in terms of, I know the presentation is focused on desal, but in terms of, do you find that traditional water treatment, there's a lot of usage of the oil and water measurement as at the water intake as well, just to make sure that you don't bring any large oil spills into the traditional water treatment as well.
Like a freshwater municipal treatment plant.
Yes, that is using surface water, I guess, to treat and.
We certainly do operate in that environment. Generally speaking, industrial facilities are going to be a much bigger user of our products, of our technology, because you're more likely to have contamination into or out of a industrial plant than a municipal plant would be. However, certainly in North America, in the United States, where we have very long rivers that have a lot of commercial barge traffic, there's plenty of opportunity for spills to occur near municipal intake systems. I live here in St. Louis, and we're right where the Mississippi and the Missouri River meet, and right in the middle of the river is the intake for the entire city. So any barge passing through there, if it has a spill, it's going to go right into the city's intake. So there, usually the municipal plants will go through some type of risk analysis and figure out, what is the chance that we're going to have a spill? What would that spill do to us if it occurred, and how long it would occur, and so forth. And if they say it's likely and it could cause us problems, then a monitor would be appropriate for them. And like I said, we certainly do have a number of them throughout the U.S., Europe, and parts of Eastern Asia for monitoring of spills for municipal plants.
Okay, makes sense. Thank you.
Sure.
I think there's in the chat, someone asked, could you explain a little more in depth as to the effects that I don't know if you've seen it in the chat.
I had not seen it in chat, no.
Yeah. Could you explain a little more in depth as to the effects that fouling has on an RO system?
Sure, yeah. Let's see, let me get back down to here. A reverse osmosis membrane has three major layers. There's my camera. There's three layers to the reverse osmosis membrane. The primary desalination layer is, if I remember, it's a polyamide layer, which is a hydrocarbon-based structure, and it's only a few molecules thick, and the structure of the molecules is such that water can pass through the lattice of the molecules, whereas salt and other things cannot. Then below that, there's a polysulfone layer, which basically is a structure that the polyamide layer can stick to. And so the polysulfone is very, very thin. And then there's a third layer that's really just a backbone or a skeleton for everything to sit on and produce a membrane that you can actually hold and put into a spiral and such. So there's two different things that can happen to a membrane. The first one is that heavy fuels, crude oil or lubricants that are very large molecules, they can put a coating on the top of the membrane. And so if there's a layer of oil on the top of the membrane, or if there's a layer of algae on top of the membrane, then water doesn't pass through it as easily. So you have to increase your pressure. Obviously, you have to increase the amount of energy needed to pass water through the system. And so your cost goes up pretty significantly for that. So a cleaning operation would be needed. Some type of acid or caustic base cleaning is needed to get all the goop off of the membranes. And the second thing that can happen is that the hydrocarbons, especially if they are very light, smaller hydrocarbons, benzene, gasoline, something like that, they can actually degrade or damage the membrane permanently. So the hydrocarbon, the polyamide layer on top can be dissolved by the by fuels, and then the polysulfone layer, which is the second layer and the thicker layer, can also be dissolved or damaged by hydrocarbons and fuels. So it's a little bit of an unknown as to actually what will happen if you have a fuel oil spill at the intake. You will have either or both a coating that needs to be cleaned off of the membranes, or the membranes themselves can be permanently damaged. And what will happen after damage is that more salt will pass through the system, more dissolved solids will pass. So calcium and sodium and all those kinds of things will pass through the membranes when they wouldn't otherwise. So your production is no longer fresh water. It is something that's got a little bit more salt into it than what you wanted. And the only way to fix this is replacement of the membranes. And so the membranes usually are all installed in parallel. So the same water is delivered to all the membranes. There might be a second train of membranes that treats the reject water to get some more salt out of it. And so the water would eventually go to those in series. But if there is an upset, when you get water that comes into it, it will be dispersed to or delivered to all the membranes uniformly. So damage to one probably means damage to all of them, either a coating or actual physical deterioration of the membranes themselves. If it's algae, it's not going to physically damage the membranes, but it certainly will coat the membranes with the plankton or the algae bodies themselves, and will need to be washed off, or some type of chemical will need to be used to clean off the membranes from the presence of the particles on them. Does that answer your question? Whoever was asked.
Well, I think it should have. I didn't see a response.
Okay.
Yes, he says it does. Yes, thank you.
Great.
All right. Any other questions, observations?
Yes, I have a question.
Yes,
sure.
go ahead, Ezekiel.
Okay. There is a lot of information out there about water gone through the reverse osmosis system and health issues. So based on your opinion and your research, how healthy you think it is for water gone through the system for human consumption? How safe is it?
You know, the details I have seen, and I am definitely not an expert on RO system, on membranes themselves. But in talking to the experts, they firmly believe that they can, eliminate pathogens and dissolve solids from water with a membrane. And so I used to live in California, and parts of California are extremely water tight. They have humongous droughts, and they have built reverse osmosis systems to clean up the sewer water and reintroduce it into, in some cases, the drinking water processes, in some cases, irrigation water. And they have had to do a significant amount of research to prove that it is safe. And I have not scrutinized that, and I certainly have not qualified to do so. But I have to trust the policymakers and the scientists that they have proven that as long as the membranes are maintained and operating properly, that they are able to produce very, very high quality drinking water. Most of the Persian Gulf region of the Middle East produces desalinated water for virtually all of their water consumption. So Dubai, Abu Dhabi, Bahrain, Qatar, all those places, Doha, Qatar, are getting, I think, in the range of 80 to 95% of their waters from desalination. So I think that is a decent testimony to the quality of the systems and ability to produce quality potable water.
Okay, thank you very much.
Sure.
Any other questions, comments?
Chip, I have one question. With respect to the source of the water for desal plants, I know some of those are more submerged intakes or deeper water intakes. Is there really still a potential for contamination, for oil and water contamination? And can we really detect such low levels if there are?
Yeah, certainly oil tends to float on water. And so the lower you put a intake below the surface, the less likely you are to see oil. So you can mitigate a lot of the oil contamination by having a subsurface intake, and the lower you go, the better off you're going to be. Some of these plants, the intake is actually below the sand layer. So they basically dig a hole for the intake, covered up with sand. So it looks just like the bottom of the ocean, but they have basically a sand filter. It's the very, very first process you go through. Not all fuels and not all hydrocarbons and oil are going to float. Benzene and other monoaromatic hydrocarbons are soluble in water, into the thousands of ppm range in some cases for benzene. And that's very temperature dependent. But if it's soluble in water, it doesn't really matter, if it can float or not, or how deep into the water column you're having your intake. It is possible to have benzene and other light hydrocarbons present in the intake, regardless of where you are. For small desalination plants, maybe at a resort, it may not be as important because the size of the membranes is not very large. But for large industrial plants or for municipal water intake, sometimes these membrane can be, $500,000 to $2 or $3 million worth of membranes, and 1 part per million of benzene could produce some significant damage to them. So there's not a significant risk to this, but there is significant costs to a fouling. So if you can prevent yourself from having issues by hydrocarbon attack, even if it's pretty unlikely because you have a low intake location, the cost to prevent and the cost associated with the fouling are pretty high. So your cost to benefit ratio is pretty good.
Thank you very much.
Sure.
Yeah. Well, that seems to have taken us to the end of our session, almost on time.
Excellent.
Would like to thank you very much, Chip, for
Sure.
At very short notice being able to give us this presentation. And I would especially like to thank Abigail Ali for making the arrangement. So thank you very much, Abigail. And the
Not a
team
problem.
for doing that. And we look forward to continued networking with you and your team. And of course, if it's Wednesday, it's CAWASA webinar. And it is where we bring you the latest in technologies and keep you posted with the cutting edge of new technologies and what's happening in the water and wastewater sector. So please continue to join the CAWASA Wednesday webinars and keep sharp with, keep honing your skills in the water sector. Thank you very much. I'm Ignatius Jha, Executive Director at CAWASA, signing off and wishing all of you a good evening, and please do keep safe and well. Thank you very much.
Thank you very much. Have a great night.
Thank you.
Hi, everyone.